Right now, you're moving through space at nearly 2 million miles per hour. Earth spins, the Sun orbits the Milky Way, and the galaxy itself drifts through the universe. Motion so vast you cross thousands of miles each minute without noticing. If you are interested, subscribe and be part of the search as we uncover the world's signals and stories written across the stars. Every person who has ever lived has done so under the light of a single star. That star, our Sun, sits about 26,000 light-years from the Milky Way's centre, tucked inside a minor spiral arm called the Orion Spur. From here, we look across a disk of stars so large that light itself needs 100,000 years to travel from one side to the other. The Milky Way is a barred spiral galaxy, a thin whirl of stars and gas shaped into glowing arms that curve outward from a bright central bar. If viewed from above, it would resemble a radiant pinwheel, its arms traced by young blue stars and luminous clouds of gas. At the core lies a supermassive black hole, Sagittarius A star, about 4 million times the mass of our Sun. It's an invisible engine. Its gravity is so intense that nothing, not even light, can escape. Gas and dust swirl around it in an accretion disk, accelerating to near-light speeds, heating to millions of degrees and releasing torrents of X-rays and radio waves. A few dozen stars trapped in its gravitational grip orbit this darkness at astonishing speed, some completing a circuit in less than 20 years. This furious centre, a place of both creation and destruction, acts as the galaxy's anchor. Without it, the Milky Way's heart would unravel. Around that heart, the entire galaxy spins once every 230 million years, so slowly that since the age of dinosaurs, the Sun has completed only a single orbit. Every revolution rearranges the positions of billions of stars, yet to us the galaxy seems frozen in time. Despite its breadth, the Milky Way is remarkably thin. If it were the size of a dinner plate, its thickness would be less than that of a sheet of paper. Within that fragile disk lie an estimated 100 to 400 billion stars, and perhaps more planets than there are grains of sand on Earth. But the galaxy is mostly empty space. If the Sun were a basketball, the nearest star would be another basketball over 2,000 miles away. The space between would contain almost nothing, a near-perfect vacuum, only a handful of hydrogen atoms drifting through each cubic meter. That emptiness defines the galaxy's true nature. What appears in photographs as a crowded sea of light is mostly darkness. Even in the Milky Way's densest regions, the average distance between stars dwarfs anything human imagination can comfortably hold. This isolation explains why interstellar travel remains the ultimate challenge. The distances are simply too great. Still, the Milky Way is far from static. It's a living structure shaped by gravity and time. Cold clouds of gas collapse to form new stars. Massive suns explode in supernovas that scatter carbon, oxygen, and iron across space. Those elements become the building blocks of planets, and eventually of life. Our own Sun is a second-generation star, born from the ashes of earlier ones. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in ancient stellar furnaces. Every living thing is a continuation of the galaxy's chemical story, matter recycled, reshaped, and illuminated. The galaxy's spiral arms are not fixed structures but waves of density moving through the disk, patterns that compress gas as they pass, sparking bursts of starbirth. The Perseus and Sagittarius arms form two of the main spirals, but our solar system lies in a quieter corridor between them. In these calmer regions, supernovae are rare and radiation levels are low, conditions that may have allowed life on Earth to evolve undisturbed. Were we closer to the galactic core, where stars crowd together and black holes feed, our planet's skies would blaze every night. but life as we know it might never have survived. At the centre, about 26,000 light-years away, Sagittarius A star marks one of the most extreme environments in the known universe. Its gravity warps both space and time. A clock near its edge would tick more slowly than one on Earth. Astronomers have observed stars slingshotting around it at thousands of kilometers per second, living experiments in Einstein's relativity. To anyone near that core, the sky would never darken. Stars would fill every angle of vision, and radiation would pour from every direction. By contrast, our position on the outskirts is tranquil, a cosmic vantage point of rare stability inside a galaxy built on violence. From inside the galactic disk, we cannot see our home's full structure directly. It's like living in a vast city but seeing only the nearest streetlights through the fog. Astronomers piece together its form using radio, infrared, and microwave observations, mapping stellar motion to reconstruct its shape. These surveys reveal something unexpected. The visible galaxy accounts for only a small part of its true mass. Surrounding the Milky Way is a vast halo of dark matter, an invisible substance that outweighs all stars, planets, and gas by nearly 5 to 1. It neither emits nor absorbs light, yet its gravity binds the galaxy together. Without this unseen halo, the outer stars would drift away, unable to stay in orbit. Dark matter is the silent framework of the Milky Way, the skeleton upon which its luminous body hangs. Even with that hidden mass, about 1 trillion times the mass of the Sun in total, the Milky Way is ordinary by cosmic standards. Some galaxies, called dwarfs, contain only a few billion stars. Others, like IC 1101, are giants spanning 500,000 light-years, with hundreds of trillions of suns. Ours sits comfortably between extremes, not the largest, not the smallest, simply one of countless spirals adrift in the cosmic sea. Every star you see with the naked eye belongs to this single galactic island. Even the brightest points, like Sirius or Vega, are part of the Milky Way's immediate neighbourhood. The hazy band stretching across the night sky is our edge-on view of the galactic disk. Billions of distant stars blending into a soft silver glow. To an observer beyond our galaxy, that entire band would shrink into a single, faint spark among billions of others scattered through the darkness. The light from those distant stars is ancient. The photons striking your eyes tonight may have begun their journey before the first cities rose on Earth, or even before humans existed. We never see the Milky Way as it is now, only as it was thousands of years ago. A reminder that every starlit sky is also a window through time. The Milky Way itself is constantly changing. Its arms twist, its smaller companions merge and dissolve, its stars drift outward over eons. Even now, our galaxy is consuming several satellites, including the Sagittarius dwarf galaxy, pulling their stars into long ghostly streams that wrap around the disk. This slow process of cosmic cannibalism is how galaxies grow, by devouring their neighbours and weaving their stars into new forms. And yet, for all its power, the Milky Way is fragile compared to the universe that holds it. It floats in a vast cosmic wilderness, surrounded by other galaxies too distant for their gravity to bind. Every discovery about it, its size, its mass, its motion, leads to the same realization. Scale is relative. The Milky Way is our cosmic home, immense beyond comprehension, yet small in the grand design. Beyond its glowing arms lies a still greater structure, one that shows just how little a galaxy truly is. We often picture our galaxy as a glittering city of stars, every patch of darkness hiding another sun. But the reality is far lonelier. Between one star and the next stretches so much space that even light, racing at 300,000 kilometers per second, takes years to cross it. Our nearest stellar neighbour, Proxima Centauri, lies a little over 4 light-years away, about 40 trillion kilometres. If the Sun were a marble resting on the ground, Proxima would be another marble placed nearly 1,000 kilometres away. Between them, almost nothing. A few lonely atoms drifting through a gulf of darkness wider than imagination. This vast emptiness defines the Milky Way. Every star, planet and comet is an island in an ocean of space. Even within our own solar system, the distances are staggering. Voyager 1, the farthest spacecraft ever built, speeds through space at 17 kilometers per second, fast enough to circle Earth in 7 minutes, yet it would need 75,000 years to reach the nearest star. That single fact shows how enormous even our small corner of the galaxy really is. Space isn't true nothingness, but it comes close. In the interstellar medium, a cubic meter of space contains, on average, only 1 atom of hydrogen. The air you breathe holds roughly 10 to the 25th power molecules in the same volume. Compared with that, the cleanest vacuum we can create on Earth would be unimaginably dense. Yet this faint mist of gas and dust is the raw material for future stars. Over millions of years, gravity gathers it into giant clouds, molecular nurseries, where hydrogen cools, condenses, and eventually ignites. The void, it turns out, is not empty. It is potential waiting to become light. In a few regions, these clouds glow as nebulae, immense, colourful structures like the Orion Nebula or the Eagle Nebula. Inside them, newborn stars carve hollows in the gas with their radiation and stellar winds, shaping vast pillars and arcs of glowing matter. But such places are rare jewels. The Milky Way is mostly darkness, punctuated by brief, brilliant sparks of creation. Between them lies the true interstellar gulf, a realm a few degrees above absolute zero, where light can travel for years before striking another particle. Distances here defy intuition. The average gap between stars is about 5 light-years, each one nearly 10 trillion kilometres. A beam of light takes 8 minutes to travel from the Sun to Earth, but 30 million minutes to reach the next star. Imagine walking across a field that stretches from the size of a neighbourhood to the width of continents. That is the scale we confront between stars. Even the galaxy's spiral arms, so solid in photographs, are mostly open space. Dense star clusters, like the Pleiades or the Hyades, contain thousands of suns packed tightly together, but they are small oases within a desert that extends for thousands of light-years. A traveller crossing those distances might pass entire lifetimes without ever approaching another sun. Astronomers describe this balance as a cosmic ecology. Stars are born in groups, drift apart, and scatter across the disk. The vast separations between them act as a buffer, preventing frequent collisions even as the galaxy churns and evolves. Radiation from ancient supernovae and energetic cosmic rays streams through these voids at nearly the speed of light. Every second, dozens of these invisible particles pass through your body, fragments of dying stars still carrying the energy of their violent birth across the Milky Way. For humanity, this emptiness is both obstacle and revelation. Our spacecraft lose power long before they can cross it. Our fastest radio messages fade into background noise after only a few light-years. Even at the speed of light, a simple hello sent to the nearest star would take 4 years to arrive, and another 4 to return. Yet the same emptiness that separates worlds also offers clarity. It is a pristine laboratory where light and gravity behave undisturbed. By studying faint distortions in starlight, astronomers can measure the composition and temperature of gas clouds light-years away. The void becomes a kind of lens, an instrument through which the universe reveals itself. Our solar system sails through this medium inside the heliosphere, a vast bubble carved by the solar wind, a stream of charged particles blowing outward from the Sun. At its edge lies the heliopause, where the Sun's influence yields to the pressure of interstellar space. In 2012, Voyager 1 crossed that frontier. Its instruments recorded a sharp rise in cosmic radiation and a subtle shift in magnetic fields, the first unmistakable sign that a human-made object had entered the space between the stars. It still drifts outward today, silent but steady, carrying with it the faint heartbeat of Earth, a golden record of our presence in a galaxy that may never notice. Though nearly motionless by our measure, the interstellar medium changes over cosmic time. Clouds drift, shock waves ripple outward from supernovae, and stars slowly migrate around the galactic center. In a few million years, our solar system will move into a new region, perhaps denser, perhaps thinner, subtly altering the balance of cosmic rays and sunlight that reach Earth. On human timescales, though, the ski appears fixed. The constellations will keep their shapes for tens of thousands of years. Their gradual drift is far too slow for the eye to see. Understanding what lies between those distant lights reshapes how we see them. Each star is not simply far away. It is separated by a gulf so vast that even imagination falters. The spaces between the stars give the galaxy its structure, the emptiness defining the light. And as we travel farther outward, this pattern repeats. Clusters of stars give way to greater gaps, galaxies to still wider voids. The deeper we look, the more the universe reveals its true design. A cosmos built mostly of nothing, where rare sparks of matter and energy trace the fragile outline of existence itself. When we look beyond the Milky Way, we find that even our vast galaxy is not alone. It is part of a small family of galaxies, a gravitationally bound collection drifting together through space. Astronomers call it the local group, a cluster of roughly 50 or so galaxies scattered across a region about 10 million light-years wide. Most of these galaxies are tiny dwarfs, faint smudges of light visible only through powerful telescopes. They orbit the two main giants of our group, the Milky Way and the Andromeda Galaxy, like small boats circling a pair of great ships. These two dominate the region, their gravity weaving the smaller galaxies into loose, elongated orbits. Between them lies an ocean of intergalactic space so vast that even light takes more than 2 million years to cross. The Andromeda Galaxy, also known as Messier 31, is our nearest large neighbour and almost a mirror of our own. It is a barred spiral, about twice the diameter of the Milky Way, containing perhaps 1 trillion stars. From Earth, it appears as a faint hazy patch in the constellation Andromeda, the most distant object visible to the unaided eye. When you look at it, you're seeing light that began its journey before humanity existed as a species. Despite that enormous distance, Andromeda and the Milky Way are on a collision course. Both galaxies are moving toward each other at about 110 kilometers per second. In roughly 4 to 5 billion years they will meet. The event won't resemble the violent crash of solid objects. Galaxies are mostly empty space. Their stars will pass through each other almost untouched, separated by distances so vast that direct collisions are extremely rare. Instead, gravity will distort and stretch both galaxies into tidal streams, flinging stars into long glowing tails before they eventually merge into a single larger system. This future galaxy, sometimes called Milkomeda, will likely be a massive elliptical, a golden spherical collection of stars without distinct spiral arms. The merger will trigger new waves of star formation as gas clouds collide and compress, briefly reigniting the cosmic furnace. Our Sun, by then nearing the end of its life, may still orbit within this new structure, circling through a sky filled with countless new suns and bright tidal arcs stretching across the heavens. Before that grand encounter, our galaxy continues to interact with smaller companions already in its orbit. The most prominent are the large and small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere as faint, detached patches of light. They are gravitationally bound to the Milky Way, slowly being drawn closer. Streams of hydrogen gas torn from them by tidal forces form a bridge connecting these galaxies to ours. In time, they too will be consumed, their stars and gas folded into the Milky Way's outer disk. Dozens of even smaller galaxies accompany us, faint dwarfs like Sagittarius, Fornax and Draco, many of which are already being torn apart. Their remnants appear as long ribbons of stars looping through the Milky Way's halo. These stellar streams are the fingerprints of galactic evolution, evidence that galaxies grow by absorbing others. The Milky Way's outer regions are a museum of these events, each arc of stars a fossil record of a past collision. Gravity is the architect of this cosmic neighbourhood. Every galaxy within the local group feels its pull, tracing invisible orbits through the shared gravitational field. But gravity is also the sculptor of isolation. Beyond our local group lies the local void, an immense, almost empty region where galaxies are rare. The border of the local group marks the reach of our combined gravity. Beyond it, the universe's overall expansion becomes stronger than our mutual attraction. On that scale, everything else is receding from us, not because it is moving through space, but because space itself is stretching. Inside our group, however, the story is one of slow convergence. Over billions of years, gravity will continue to draw its members together. The dwarfs will merge into the giants, and eventually Andromeda and the Milky Way will unite at the group's centre. Around them, the remaining galaxies will orbit like debris around a massive luminous core. The local group will become a single larger galaxy drifting in the darkness, a bright island isolated by the expanding universe. This process may sound destructive, but it is natural and continuous. Every large galaxy we see today is a product of countless mergers. The delicate spirals we admire are only temporary forms in a long history of transformation. Galaxies grow, age, and evolve just as stars do, not in years or centuries, but in epochs spanning billions of years. Our understanding of this neighbourhood has expanded dramatically in the last century. Early astronomers once thought the Milky Way encompassed the entire universe. Only in the 1920s did Edwin Hubble prove that Andromeda was not a nebula within our galaxy, but a separate galaxy altogether. The first evidence that the cosmos extends far beyond our own. That discovery changed everything. It revealed that the Milky Way, once imagined as all of creation, is merely one of countless galaxies scattered through infinite darkness. From that perspective, the local group is not a vast domain, but a tiny pocket of the observable universe. Beyond it lie superclusters, titanic assemblies of thousands of galaxies, and beyond them, the cosmic web, where filaments of matter stretch for hundreds of millions of light years. But those immense structures are for later chapters. Here, in our small neighbourhood, we see the immediate forces that shape our future. The slow dance of galaxies, the constant reshaping of form, and the quiet persistence of gravity across unimaginable time. If we could look ahead 5 billion years, the night sky would bear little resemblance to the one we know. Andromeda would grow larger each century, first a faint smudge, then a glowing arc filling the heavens. When the galaxies finally merge, future observers, if any remained, would watch vast streams of stars stretch from horizon to horizon. The Milky Way would no longer exist as a separate entity. Its identity, like ours, would merge into something new. And yet, the physics remains the same. Even in that far-off age, gravity will continue its slow choreography, shaping light and matter into new designs. Galaxies will keep forming, merging and fading. The local group, now a single great system, will drift alone into the expanding void, a glowing relic of the age when the universe was young. Beyond the local group, gravity organises the universe into structures so immense they defy direct comprehension. Our small collection of galaxies drifts within a much larger realm called the Virgo supercluster, a sprawling expanse that stretches across more than 100 million light-years. Within it lie thousands of galaxies, bound together not by visible bridges but by the invisible pull of gravity threading through space. At its heart sits the Virgo cluster, an enormous congregation of more than 1,300 galaxies. Some are spiral systems like the Milky Way, but most are elliptical giants, smooth, oval-shaped collections of old stars glowing faintly in golden light. These galaxies swarm around one another at speeds reaching 1,000 kilometers per second, moving through hot gas that fills the cluster's interior. This gas, heated to tens of millions of degrees, shines in X-rays, revealing a web of plasma stretching between galaxies. Yet, by visible mass alone, the Virgo cluster shouldn't exist. The stars and gas we can detect account for only a fraction of the gravity required to hold the cluster together. Without an additional unseen component, the galaxies would have long since flown apart. This invisible scaffolding is dark matter, a mysterious form of mass that doesn't emit or absorb light, but exerts gravity. Measurements show that dark matter outweighs normal matter by roughly 5 to 1, forming enormous halos around every galaxy and connecting them in vast filaments that span intergalactic space. In this way, dark matter acts as the hidden framework of the cosmos. Where it accumulates, gravity draws in gas, which cools and condenses into stars and galaxies. Over billions of years, this invisible architecture has shaped the visible universe, turning random chaos into intricate structure. We can't see it directly, but we can trace its presence through gravitational lensing, the way massive objects bend and distort light from background galaxies. Observations of these distortions map the unseen mass, revealing networks of dark matter stretching between clusters like strands of cosmic silk. Our local group lies on one of these strands, a small branch of a colossal web that extends far beyond the Virgo cluster. In 2014, astronomers charted this region in unprecedented detail and discovered that the Virgo supercluster is only part of an even larger structure known as the Laniakea supercluster, meaning immense heaven in Hawaiian. This supercluster spans roughly 500 million light-years, encompassing more than 100,000 galaxies, all flowing inward toward a gravitational focal point called the Great Attractor. The Great Attractor is not a single object, but a region of deep gravitational influence located roughly 150 million light-years away, near the constellation Norma. It bends the motion of galaxies over enormous distances, including ours. The Milky Way, Andromeda, and thousands of nearby systems are all drifting toward it at about 600 kilometers per second. Even as the universe expands overall, local gravity creates rivers of motion that flow inward toward the densest regions. Our entire cosmic neighborhood is caught in that current, slowly falling toward the unseen mass at the heart of Laniakea. When astronomers map these galactic flows, the result resembles a three-dimensional ocean current chart, with galaxies moving like droplets in a vast invisible tide. The boundaries of superclusters aren't walls but transition zones where the direction of motion changes, like watersheds dividing rivers on a planetary surface. Laniakea itself connects to other enormous structures, forming part of a still larger complex sometimes called the Pisces-Cetus supercluster complex, a network of superclusters extending over 1 billion light-years. If we step back far enough, the universe begins to reveal an astonishing pattern. Galaxies aren't scattered randomly through space. They form a vast interconnected cosmic web. Long filaments of galaxies stretch for hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters form. Between these filaments lie enormous cosmic voids, regions so empty that entire superclusters could fit within them without encountering a single galaxy. Computer simulations of the universe's evolution, such as those from the Millennium simulation or the Illustris project, recreate this cosmic web in remarkable detail. Beginning shortly after the Big Bang, slight irregularities in the density of matter grew under the influence of gravity. Dark matter clumped first, forming invisible halos. Normal matter followed, cooling and condensing along the same filaments. Over billions of years, this process produced the universe we see today, a vast network of glowing galaxies tracing the shape of unseen matter. Each filament is like a cosmic highway, channeling gas, stars and galaxies toward the densest intersections. These intersections become galaxy clusters, the universe's great cities. In contrast, the voids between them are the deserts, cold, dark and nearly empty. The largest known voids, such as the Botez void, span hundreds of millions of light years and contain only a few dozen galaxies within a volume that should hold thousands. Inside them, the night sky would appear almost empty, even through the best telescopes. What holds this vast web together is gravity, but what drives it apart is something even more mysterious: dark energy. This unseen force, discovered in the late 1990s, acts as a kind of cosmic pressure that accelerates the universe's expansion. On scales smaller than superclusters, gravity dominates, binding galaxies and clusters together. But across larger distances, dark energy wins, pushing the cosmic web outward, stretching its filaments thinner with time. The balance between these two forces, gravity and dark energy, defines the structure of the universe. Gravity creates the web, dark energy pulls it apart. Over billions of years, clusters and superclusters will become more isolated as space between them expands faster than light can travel. Eventually, only the galaxies bound together by local gravity, like our future merged system of the Milky Way and Andromeda, will remain visible. The rest will drift beyond our cosmic horizon, their light forever unreachable. In the present, however, we live at a special moment in cosmic history. The web is fully formed yet still visible. We can trace its strands, measure their motions, and map the architecture of existence. When astronomers point the Hubble Space Telescope at what appears to be an empty patch of sky and leave it collecting light for days, it reveals thousands of galaxies where the eye saw nothing. Every pixel becomes a window into deep time, each galaxy a city of stars shining across billions of years. Seen together, these galaxies outline the framework of the universe itself. The cosmic web is not just structure, it is history made visible. Every cluster marks a region where matter once clumped a little more densely than average. Every void marks a place where matter was slightly less abundant. The pattern we see today is the frozen echo of quantum fluctuations that occurred a fraction of a second after the Big Bang. Our Milky Way, our Sun, even our planet are part of that pattern, local ripples in a cosmic network that stretches across everything. The atoms in our bodies were shaped by this structure. Hydrogen formed in the Big Bang, heavier elements forged in stars, all distributed along filaments of dark matter that guided their flow. We are not just in the universe, we're expressions of its large-scale geometry. If we could step outside the universe and look down upon it from some impossible vantage, we would see a delicate lattice of light, galaxies strung along vast filaments, glowing softly against an endless darkness. It would look less like a random scattering of points and more like a living organism, a web of veins or neurons connecting every part of existence. The same laws that govern the smallest particles of matter also govern this grand architecture. From quantum fluctuations to galactic superclusters, the universe builds complexity through repetition, symmetry, and time. And within that web, our galaxy, so vast to us, is just one luminous dot, one node among trillions. Its light, its history, its collisions and its life are all part of a structure far greater than anything the human mind evolved to comprehend. Yet somehow we can map it, describe it, and understand its origin. From the vast strands of the cosmic web to the spaces between its threads, everything we see, every planet, star, and galaxy, traces the same invisible scaffolding. And as we look outward into that immense structure, one realization becomes clear. The Milky Way, for all its brilliance and motion, is a mere filament in an endless cosmic tapestry, a single gleaming thread woven into the infinite fabric of the universe. If the Milky Way is a city and the local group a province, then the cosmic web is the continent, and beyond that lies the visible edge of everything. The observable universe is the largest structure we can meaningfully talk about, the full sphere of space and time from which light has had enough time to reach us since the birth of the cosmos. That boundary lies about 46.5 billion light-years away in every direction. The number seems paradoxical. The universe is only 13.8 billion years old, so how can we see farther than 13.8 billion light-years? The answer lies in the expansion of space itself. As light travels toward us, the universe stretches, carrying distant galaxies farther away, even as their light continues its journey. What we see today is not where those galaxies are now, but where they were billions of years ago. Every direction we look is a look back in time. The light from a star in Andromeda shows us that galaxy as it was 2.5 million years ago. A quasar 10 billion light-years away reveals the universe as it was when galaxies were just beginning to form. And at the outermost limit, the faint microwave glow that surrounds us comes from a time before any stars or galaxies existed at all. That glow is called the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. It's the oldest light we can ever observe, released when the universe was only 380,000 years old. Before that moment, the cosmos was a hot, opaque plasma of particles and radiation. Light couldn't travel freely, it was constantly scattered by electrons. But as the universe expanded and cooled, atoms formed, the fog cleared, and the first photons began to stream across space. The very photons we still detect today, stretched by cosmic expansion into faint microwaves. The CMB fills the sky evenly, a nearly uniform bath of radiation just 2.7 degrees above absolute zero. When satellites like COBE, WMAP, and Planck mapped it in detail, they found minute variations, fluctuations in temperature as small as 1 part in 100,000. Those tiny differences represent the earliest seeds of structure, slightly denser regions that gravity would later amplify into galaxies, clusters, and the cosmic web itself. In other words, every star, planet, and living being ultimately traces its origin back to those faint ripples in the afterglow of the Big Bang. Between the CMB and our time lie the full epochs of cosmic history. After the first atoms formed, the universe entered a period known as the Cosmic Dark Ages. No stars yet burned. Only neutral hydrogen filled the expanding space. For hundreds of millions of years, the cosmos was dark and silent, its energy locked in invisible matter and cooling radiation. Then gravity went to work. Tiny overdensities grew, drawing gas together until the first stars ignited, brilliant short-lived giants that flooded space with light and ultraviolet radiation. Their formation ended the Dark Ages and began a new era, cosmic reionization, when light once again filled the universe. The first galaxies took shape, gathering into clusters along the dark matter filaments. By the time the universe was 1 billion years old, The basic structure we see today, stars, galaxies, and vast voids, was already in place. From that moment on, the story became one of expansion and evolution. Galaxies merged, grew, and evolved. Stars lived and died. Heavier elements spread through interstellar space, setting the stage for planets and eventually life. Yet the universe itself continued to stretch. The light from distant galaxies became redshifted, its wavelength stretched by expansion until it shifted from visible to infrared, then to microwave, and eventually beyond detection. The farther we look, the redder and older everything becomes, until we reach a distance where the light has been stretched almost infinitely. That is the cosmic horizon, the limit of what we can ever see. Beyond that horizon, there may be much more universe, perhaps infinitely more, but it is forever beyond our reach. The expansion of space is so rapid at those distances that even light cannot bridge the gap. We can calculate and imagine what lies there, but we will never observe it directly. The edge of the observable universe is not a wall, it is a horizon defined by time and motion. Within this horizon, the scale of existence is staggering. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. In total, there are more stars than grains of sand on every beach on Earth, and each one may host its own worlds, its own histories, perhaps even its own forms of life. And yet these countless suns make up less than 0.1% of all that exists. The rest is dark matter and dark energy, unseen yet dominant. If we could travel outward at the speed of light, we would pass through time as much as space. First past the Milky Way's neighbours, then the Virgo cluster, then the filaments of Laniakea fading into the background. After billions of years, we'd see the universe grow younger before our eyes. Galaxies would appear smaller and bluer, their light compressed by our approach. Eventually, we would reach the era when the first galaxies were just forming, the universe only a few 100 million years old. Then, as we travelled further still, stars would vanish entirely, replaced by the soft, uniform glow of the CMB, the final visible surface of the past. Beyond that, there is no more light, only the quantum fog of the beginning itself. That beginning, the Big Bang, is not an explosion in space, but the expansion of space itself. It happened everywhere at once, every point in the universe expanding from every other. There is no centre and no edge. The cosmos is the same in all directions, infinite or nearly so. The term Big Bang describes not a moment of detonation, but the unfolding of existence from a hot, dense state to the vast structure we see today. Even now, the universe continues to expand, and that expansion is accelerating. Distant galaxies recede faster and faster, driven by the mysterious force called dark energy. In the far future, hundreds of billions of years from now, most galaxies will have moved beyond our observable horizon. The night sky will grow emptier, the cosmic web will thin, and for civilizations that might exist then, the evidence of a larger universe may be lost entirely. We live then in a uniquely privileged era, one in which the universe is both old enough to have formed structure and young enough that we can still see its beginnings. We can trace our origins back across nearly 14 billion years of history, from the atoms forged in stars to the light released in the first moments of creation. Every observation, every photon carries a message from that past. When we look into the night sky, we are not seeing a map of space, but a timeline. Each point of light is a memory, each galaxy a record of an earlier universe. The cosmos before us is both ancient and alive, constantly expanding yet eternally linked to its origins. And somewhere within this immense visible sphere, amid 2 trillion galaxies and uncountable stars, is a small spiral galaxy on the edge of an ordinary supercluster, home to a star and a handful of planets, where one species has begun to understand what all of this means. At the edge of the observable universe, light fades into silence. Beyond that horizon, there is no data, no photons, no signals, only equations, models, and imagination. And yet, the laws of physics allow us to peer, in theory, into what may lie beyond that invisible boundary. The first truth is simple. The observable universe is not the entire universe. It is merely the region from which light has had time to reach us in 13.8 billion years. But space itself has been expanding throughout that time. The regions beyond our view are still there, continuing to evolve, filled with galaxies whose light has not yet arrived and never will. Astronomers estimate that the entire universe could be at least 250 times larger than the observable part, and possibly infinite. Infinity is not a concept the human mind handles easily. In an infinite universe, every pattern, every arrangement of matter must repeat. Somewhere, unimaginably far away, there could be another region identical to ours, another Earth, another Milky Way, another you, existing in a slightly different branch of cosmic history. These are not fantasies but consequences of simple geometry and physics if space is truly infinite and uniformly filled with matter. The idea of beyond also raises a deeper question. Did the universe have an edge or a beginning in space? The answer, according to Einstein's general relativity, is no. The universe has no edge in space, only in time. It is curved, finite in volume yet unbounded like the surface of a sphere. If you could travel in a straight line long enough, you might eventually return to your starting point, not because space loops back sharply, but because it bends. The universe contains itself. At smaller scales, quantum mechanics complicates this picture even further. During the earliest moments of existence, less than a trillionth of a second after the Big Bang, the universe is thought to have undergone a period of cosmic inflation, a sudden, exponential expansion driven by an unknown field of energy. In that instant, space may have expanded faster than light, smoothing the universe and stretching quantum fluctuations into the seeds of galaxies. But inflation, if it happened, might not have ended everywhere at once. In some regions, the process could still be continuing. This leads to one of cosmology's most intriguing possibilities, the multiverse. In this view, our universe is just one bubble in a vast, eternal froth of space-time, where new universes constantly form as old ones expand. Each bubble might have different physical laws, constants, or dimensions, infinite variety arising from the same underlying physics. We cannot test this idea directly, but mathematics hints at its plausibility. Quantum fluctuations, when magnified by inflation, could spawn whole new regions of space. Some physicists compare it to a growing foam, where every bubble is a universe with its own version of reality. In one, gravity might be stronger. In another, atoms might not even exist. Most of these universes would be sterile, lifeless, and dark. But the laws of probability suggest that some, like ours, could support complexity, chemistry, and consciousness. If true, the multiverse would change the meaning of scale entirely. It would make our observable universe just one page in an endless cosmic library, each page self-contained, each story governed by its own physics. In that light, even the Milky Way's 100 billion stars become a local detail in a structure without end. But there may be limits deeper still. The Planck scale marks a boundary beyond which our understanding of space and time breaks down. Below this scale, gravity and quantum mechanics collide in ways no current theory can fully describe. The very fabric of reality becomes uncertain, bubbling with fluctuations so intense that space and time may lose their ordinary meaning. To go beyond that frontier would require a unified theory, something physicists call quantum gravity. that could reconcile Einstein's curved space-time with the probabilistic world of quantum fields. The search for such a theory has led to new ideas. String theory, which imagines that all particles are tiny vibrating strings existing in up to 11 dimensions, and loop quantum gravity, which describes space itself as a network of discrete loops, like a woven fabric of finite threads. These are not yet proven, but they hint that the universe may be both continuous and granular, infinite in extent yet quantized at its core. Beyond even that lies a deeper philosophical horizon. Why does anything exist at all? Science can trace the sequence, from quantum fluctuations to stars and galaxies, but the reason for existence itself remains outside physics. Some theories propose that universes arise naturally from the laws of probability, that existence is the default state of mathematics. Others argue that asking why presumes a cause where none is needed. The universe simply is. What we can say with confidence is that the cosmos operates by consistent, discoverable rules. Those rules apply everywhere, from the orbit of a moon to the motion of entire galaxies, and they have remained constant across 13.8 billion years of cosmic history. That consistency is what allows us, tiny creatures on a small planet, to understand events occurring trillions of kilometers away and billions of years ago. Still, even the most precise theories carry limits. We cannot see beyond the cosmic horizon. We cannot test what came before time began. We cannot reach beyond the Planck scale. Every answer uncovers deeper questions, and perhaps that is the nature of knowledge itself, an endless horizon receding as we approach. If the observable universe is a sphere of light, then the limits of scale mark the darkness beyond it. Yet that darkness is not emptiness. It is mystery, the place where curiosity begins. In the end, the more we learn about the universe, the more we understand how little of it we truly occupy. Our galaxy is one among trillions, our observable region, one among countless others, our moment, a flicker in cosmic time. And yet, from within that fleeting moment, we can look outward and piece together the story of creation itself. The limits of scale remind us that knowledge has boundaries, but wonder does not. Beyond every horizon lies another, and the act of reaching for it, of asking what's next, may be the universe's most remarkable creation of all. After travelling across the universe, from the sun's orbit to the farthest galaxies, from atoms to the cosmic web, we arrive back where we began, on a small planet orbiting an average star. From here, everything we have seen exists only as light. Yet within that light lies the story of the universe itself. The scale we've uncovered is staggering. The Milky Way spans 100,000 light-years. The local group stretches 10 million. The Laniakea supercluster reaches 500 million, and the observable universe extends 46 billion light-years in every direction. But the true measure of these distances is not their size, it is what they reveal, that everything we can see is part of a single connected whole. The same physical laws shape every level of reality. The gravity that holds you to Earth is the same force that binds galaxies into clusters. The nuclear fusion that powers the sun is the same process that forged the first stars. The atoms in your body, hydrogen from the Big Bang, heavier elements from ancient stars, are pieces of cosmic history, recycled and reassembled over billions of years. You are quite literally a small part of the universe that has become aware of itself. Seen this way, small no longer means insignificant. The universe may be vast beyond comprehension, but consciousness, even localized in one fragile species on one small planet, gives that vastness meaning. Scale alone doesn't define importance, understanding does. When we observe the cosmos, we are the cosmos observing itself. This perspective changes how we see everything. The distances that once seemed impossible become stages in a single story. The birth, growth, and transformation of matter into complexity, life, and awareness. Every galaxy, every world is another verse in that story, another attempt by the universe to know itself. Our galaxy is one thread in a cosmic tapestry woven from light and time. It is neither large nor small, ancient nor young, simply one moment in an ongoing evolution that began nearly 14 billion years ago. One day, the Milky Way will merge with Andromeda. Stars will die, new ones will be born, and eventually even those will fade. The light of our galaxy will dim until only the faint glow of red dwarfs remains. And yet, somewhere within that vast timescale, for a brief instant, it produced beings capable of looking up and asking why. Every time we look at the night sky, we are looking into the past, but we're also seeing a reflection of ourselves. The elements of our bodies were made in those stars. Their fates foreshadow our own. The carbon that carries our thoughts, the iron that flows in our blood, the calcium in our bones, all of it was once light in a dying star's final breath. The universe writes its story not in words but in atoms. Understanding this doesn't make us smaller. It makes us part of something immense. We are connected to the first galaxies, to the afterglow of creation, and to the deep future that will unfold long after our species is gone. The same patterns that shaped nebulae and clusters shape the neurons in our brains. The same mathematics that govern superclusters govern the spirals of DNA. To know this is to realize that the universe is not a distant spectacle. It is home. The Milky Way, for all its enormity, is our address, a temporary point within an infinite process. Our galaxy will someday disappear into a larger one, and that larger one will eventually drift alone in the expanding dark. But the knowledge we've gained, the ability to trace our origins from the first light to the present, will endure in the record of what we've built, and perhaps in the echoes of the signals we've sent into space. When we speak of being small, we often imagine it as a measure of power or importance. But on the cosmic scale, smallness is inevitable. What's extraordinary is that something so small can comprehend the whole. In a universe 93 billion light-years across, intelligence, fragile, temporary and local, has arisen to map the structure of everything. That act of understanding is, in itself, a kind of cosmic event. The galaxies will keep drifting, the light will keep fading, and one day, all that remains may be the record of what once wondered at the stars. But wonder, once born, cannot be undone. It is as much a part of the universe as gravity or light, a force that pulls the mind outward, toward infinity. The more we learn, the clearer it becomes. Our galaxy is small, our planet smaller still, but through awareness, we are vast. Every discovery, every observation, every question expands the universe not outward, but inward within us. The Milky Way is just one of trillions, but to understand even one is to glimpse the nature of them all, and to know, however briefly, that we belong to something far greater than ourselves. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.